Ladies and gentlemen, welcome back to Perception Paradox, and today we're diving into a very interesting topic. I've recently connected with Dr. Fred Jordan, who is the CEO and co-founder of Final Spark, and his team is exploring an audacious solution to one of AI's biggest challenges, power consumption. And instead of traditional silicon, they're using living neurons as building blocks for a new generation of bioprocessors. The goal for today is actually to understand how do they do that, what Final Spark is building, and why it's a critical path forward. And yeah, get ready and expand your perspective of what's truly possible. Let's dive in. Real people, real stories, and real challenges that break the status quo. I'm your host, Živile, and welcome to Perception Paradox. Fred, welcome to Perception Paradox.
Thank you for inviting me.
And you are just back from your vacation in the water, windsurfing. What a coincidence. Did you have some good winds?
Well, I had some wind, and that was okay. Anyway, if I'm on the sea, just windsurfing, I'm just already happy, so it's okay.
Yeah, that's amazing. I'm really grateful to have you today on Perception Paradox podcast. And well, you're a scientist, engineer, and you've been entrepreneur, and you've been working on so many cool things, and at the same time you're so much ahead into the future. Maybe you could share with us your journey. How did you find yourself in this point of life, working with the brain neurons and being so futuristic?
Well, the fact is that I love science fiction. Since I was a kid, I always loved science fiction. So the trajectory in life was always read science fiction and just imagine things that could be incredible. And I had the opportunity to make a Ph.D. in signal processing. I love science. I love engineering. I'm not very smart, unfortunately, but I work a lot. It compensates, and created a first company that was still running with a friend, using actually signal processing to analyze pictures taken with the smartphone to make the difference between counterfeit products, so fake product from China. So you take a shoe, you want to know if it's the real one or something which is fake one. You take the app, take a picture, it tells you if it's genuine or not.
Okay.
And this was using mathematical tools. And this company is doing well since 25 years. And at some point, we thought that we really love fundamental research. So we created another company called Final Spark, but about 10 years ago, to say, okay, let's make a revolution in AI. Okay. So we are two of us. Let's believe we can do this, all right? And so we started to work on this in artificial intelligence, but in directions and using tracks which are totally unusual, that big companies are not taking. And one of these tracks led us to biocomputing.
Okay, and you're using living human neurons as computer and processors. Is it right? What does that even mean, actually?
Well, it's absolutely correct. So what we do indeed is that we create so-called brain organoid. So an organoid, okay, it's like an organ. Okay, an organ is a living collection of cells. Okay, so we create an organoid, which is a small nervous tissue, like 0.5 millimeter of diameter, made of neurons, human neurons, as you said, you're right. And we try to interact with it in order to program it so that it can perform computation and information processing for us.
Hearing you right that you're literally growing brain tissue in a lab and using it to compute?
Yes, exactly this. Yeah.
That's insane. How did that start? Like, how did you got to this point? Because it does sound very like sci-fi movie scenario.
Yeah, and this is why we love it, by the way. But it was a bit, I would say, by luck and by chance, because we were already working in Final Spark. And you know how ChatGPT is working? You know about artificial neurons?
a bit, but I think you could explain that for us and for the
Right.
wider audience.
Okay, so most of the AI today, okay, is based on using so-called artificial neurons. So artificial neurons is just very, very crude and simple simulation of neuron. Okay, just a weighted summation of the input gets the output. Very, very simple. Okay, but ChatGPT works this way. All what you find in AI works this way. Okay, so we started to work on some types of simulations of neurons, digital simulations, which were more realistic. So in our brain, it doesn't work this way. Neurons are way more sophisticated. So we wanted to have a model which is closer to the reality. And we did it. Okay. We made collections of simulation of neurons connected, which were more realistic. The problem is that they were consuming kilowatts of power for a few hundreds of neurons, knowing that your brain has 100 billion of neurons.
Yeah.
And just by chance, we had an employee who was working at the Swiss Federal Institute of Technology in the lab of Professor Markram. He was working here. He was forced, actually, for his military service to work in this lab. Okay, so there was no correlation, no relation with the final spark at all, okay, whatsoever. And he was working actually in this lab with real neurons, real human neurons. And he was talking about to us how slow or how low energy these biological neurons were consuming. So on one hand, we had a very efficient neuron, which was the biological real one, and we had a very inefficient neuron, which was the simulated one. So, and we made the connection this way, okay? So, okay, if we want to be realistic, instead of trying to simulate it for orders of magnitudes or more of watts, let's take the real thing. That was like, I mean, from an engineering perspective, it was rational.
Okay, and where those human neurons are coming from? How do you get them? Like, and ethically, and where does the ethics come in?
So what we use initially cells from your skin.
Okay.
From cells of your skin, it's possible, thanks to the Nobel Prize Yamanaka, to convert them into stem cells. Once we have the stem cells that we receive here in our lab, which is just below here, and we are able to convert these stem cells in any type of cells of your body. And of course, here we focus on neurons. So we differentiate these stem cells into neurons, and then we connect the neurons together to create small nervous tissue, and then we put them on electrodes.
Okay. And then how do you actually make it work? How do you program or train the tissues, those living tissues you mentioned, to perform computational tasks?
You want to know this, okay? And we are both. I also want to know it. So I share your same curiosity on how you program them, okay? And I don't know, and nobody knows, okay? At this point, okay? I can tell you what people think might work and what people are trained, and including us, okay? So I would say basically there are two directions that we are trained, and there are only two directions that are known so far, okay?
Yeah.
One thing is by interacting, as we are doing right now, you and me. Maybe you are learning something by interacting with me. But at the end of the day, what we are doing together is that I'm basically sending spikes to your nervous tissue, and you are sending spikes to mine. Fundamentally, if you have a brain connected with electrodes, I can do exactly the same thing as what we are doing from an information transmission perspective. So that means that if you are able to send electrical signals to a collection of neurons and receive their answer, you are able to make a communication, and you are able to modify the system so that it learns something. This is known to work. This is working with you right now. Okay, so this is one direction. And the other direction, which is a bit different, is conditioning. Very well known. You have a dog, you want to train it. You give sugar.
Yeah.
It works. Known to work since ages, all right? So you can do the same. For instance, what we do is we are using neuromodulators like dopamine that we are releasing directly on the neurons. So if they do what we want for a given input, then we can reward them with dopamine.
Okay.
And then you have a closed loop systems like I try, you do well, you're rewarded. You're not rewarded. And then you do it again. So at the end, you're supposed to converge in something that has learned something.
Okay. And you also, I was checking your website. So you have on your website a feature that you can see the spiking of neurons in real time, right? So what exactly am I seeing when I go on the website, and how does that translate into your computation?
But you're right. That's the good thing to look at. I encourage any of the people viewing or listening to this video to go on the website indeed and go to the live section. So what you can see here is actually the live, real-time electrical activity coming from the electrodes connected to the organoids that we have here, just one floor below me.
Wow.
So
okay.
for each brain organoid, we have 8 electrodes, and each of these 8 electrodes, we record 1 second of activity and we stream it on our website. And we do it every second. The way the neurons work is that they create so-called action potential, which is a small spike of activity of a few, I'd say 100 microvolt. And you can see this spike of activity. If there is no spike, maybe actually the brain organoid is actually dead. And this is one of the definitions of death, actually, when there is no electrical activity in the nervous system. But if you see a lot of activity, consider that most of the time these are spontaneous activity. That means the neurons talking to themselves. Okay, like you see the brain organoids dreaming, if you want. And sometimes you may see some very strong spikes. These are actually stimulation that comes from the researchers and that want to change the behavior of the spontaneous activity or the behavior of the response they get.
You've been working on that for the last 10 years?
No, actually, we've been working on FireSpark for the last 10 years, you're right. But in biocomputing, that means where computers are doing computing with living neurons for the past 5 years.
Okay, for the past 5 years. So what's your big vision right now? What are you aiming to achieve with this research and work you're doing daily?
Well, ideally,
We can
I would imagine cloud computing, but bio-cloud computing. Instead of having server computer, you would have a bio-server computer, like Amazon Web Services, but using living neurons, and typically providing AI services. Because AI is based on using artificial neurons, so we would still provide AI, but using biological neurons.
Okay, and how would that affect the experience of then using AI if that, let's say, succeed what you're working on?
I would say ideally, it would not affect experience.
Okay. Then why would we need to change towards that?
I was waiting for this. But it would reduce the electrical power bill by 100.
That's a strong statement.
Yeah, because you have to consider that compared to a simulation of a biological neuron, the real one is about 1 million times more efficient. That means your 100 billion of neurons that you have in your brain with 10,000 connections per neuron consume about 20 watts. But if I wanted to simulate your brain, I would need a small nuclear plant today. This is and basically when you use AI, basically you are simulating neurons. So this is why we expect a very huge gap in power efficiency. And it's no surprise. It's normal. I mean, we are the result of hundreds of millions of years of evolution when life was obsessed with energy efficiency. Okay, so there is no merit by using something which has been so optimized, for hundreds of millions of years to say, okay, it's efficient. Of course, it had to be efficient.
That is so cool. And can you please share how is that different from putting for example, the chips in people's brains? Because also there was a stream of that direction, that taking the data and I think and computing from the chips.
So you mean putting the chips in the brain?
Yeah.
Well, it is totally different because when you do these kind of things, as you propose, you are doing in vivo experiment.
Hmm.
Already from a regulatory perspective, you are falling in a big thing. In our case, we are very much free in all experiments that we can do because we are entirely in vitro. So on our side, we are really thinking about a living machine. Okay, this is what we are trying to do. And there may be some usefulness for in vivo experiments of what we are doing, but this is not our major focus.
What are the major challenges you're facing by overall communicating and going with those human neural tissue and this basically living computing in the ecosystem? Do you experience more support or more contradictory questions?
No, I would say quite a lot of support actually.
Huh?
First from the scientific community, we have many universities using our brain organoids actually remotely. So we give free access to some elected projects. So we have many people working on trying different things on, so we can 24/7 they are booked by universities.
Wow. Okay, that's pretty cool.
We now stopped. We don't accept more universities. We have too many. And we have also even companies renting access. Okay, so to make their own experiments. So I would say there is a good interest, and also people like you, okay, who say, well, this is fascinating. This looks
Hmm.
like possible or science fiction. Is this even serious? And yes, it is. I mean, this is this is for real. And so I love actually the way and the direction it takes. Um, it's it's a kind of vision of the technology which is a bit disruptive
Hmm.
because technology always meant in the past artificial things,
Yeah.
but this is not artificial. This is living. This is a kind of mix, just in between, and this is what is fascinating here.
Do we have any ethical contradictions here when it comes to humanity technology? We already have a lot of contradictions, right, with the overall artificial intelligence and robotics, humanoids taking over. And how is that in your case?
First, each time there are disruptive things coming like AI or biocomputing, of course, there is ethical discussions. But here, it's even more critical because we
Hmm.
are talking about something which is as intimate as our own, neurons, human neurons. Okay, this is really the heart of our system. So we recognize this very early.
Okay.
So what we do is that we have set up a collaboration with different universities in philosophy. So these are ethicians, okay? These are experts in this, not us. Okay? So, and what we do is that we give the science, and the idea is that we should have a number of publications coming, I hope, this year in philosophy about what is the ethical impact of using brain organoids for computation in the future.
Mm. That sounds very interesting. Okay. And one more thing. I found in one of the interviews you did a very fascinating fact. You mentioned that it's possible potentially to use a biocomputing for space exploration, and it's a very interesting trajectory. Can you share a bit more how that would actually could function in the space environment?
Well, first, these ideas of using for space exploration was not coming from us, but from people who came to us said, "Well, this could be used for space exploration." Okay,
Huh.
and that was, I think potentially you could refine those systems instead, and use them for space exploration. We are just at the beginning of thinking about what could be the applications of living, well, in between living and artificial systems used for space exploration. But I think it's a very totally innovative direction. We can modify these neurons maybe in a way that make them more robust to ionization constraints, for instance, things like this. This is one direction which is considered.
What are the other ones? I saw something also when it comes to the medical, personalized medicine implication could be a possibility.
Yes, personalized medicine is probably the most obvious one if we talk about medical application or therapeutic applications, because we can take a patient, develop neurons from having exactly the same DNA as him or her. So therefore, we can really perform experiments on the very same neurons that the person has in the head. And for screening, for testing drugs of side effects, effectiveness, this is just the perfect tool indeed. Yeah. And many people don't believe in this, and our platform, Neuron platform, is also built in this direction, enabling to perform some such experiments.
Okay, that sounds fascinating. So, what are the major focus right now for the Final Spark growth and your experiment?
The main thing is training, okay?
Uh-huh.
Training, so getting the output that you want for a given input. And there is also lifespan, so to make the neurons live longer and longer, okay? There is also the size, okay? Right now, the brain organoids that we have are, the maximum are a few millimeter of diameter, and we want to be big, okay, to go big. We want also to have to assemble different types of area of the brain and connect them. And these are called assembloids, and we are working on it. So this is some of the directions, and probably add other way to release neuromodulators to the system as we are doing.
Okay, that's amazing. And I think we can follow it on your website as well and online communication. But tell me, Fred, I also have a bit of a personal question for you. So you've been going through different career paths, building businesses, science, etc. And then 3 years ago, you found neurobiology, right? It was not always in your interface, in your focus. How did that basically happen? And what drove you to completely, no, I wouldn't say completely reinvent yourself, but to actually a bit dive into such a complex and interesting field?
Yes, I think it's a very interesting observation that you make here. You're right. Because my thing, and the same for the co-founder of Final Spark, we were really into programming, and mathematics. Nothing in biology, okay? Not even close, zero, okay? So we had to start from scratch, and it was a wonderful journey, okay? Because we started like a child, okay? And so we had to take courses about basic biology, cell culture. You take a pipette, you don't know, you do cell culture. You have to manipulate cells, okay, in a laminar flow hood, okay, with a coat, I don't know, with gloves and everything. So we didn't know anything, okay. So we had people who taught us about doing this, and I was very impressed by it. People were happy to show us. They could have said, well, these people are just mad, okay? But no, they showed us, okay? So we worked with a number of neurobiologists, more and more talented people. We showed us all the details of our cell culture and then how to connect with electrodes and all the things, to the point we were able actually to grow our own brain organoids and publish in Frontiers in neurobiological review. So that was really cool, starting from scratch. It just shows that you can start from scratch and go to the expert level. If you just take the time and you're really interested, you can do it. I mean, it's okay.
Yeah. Did you, during the last few years, did you ever have a challenging moment when you thought, oh, I think it's over, I'm just gonna quit? Or you pushed through?
No. It was more like at some point, particularly in the beginning, we felt just like ridiculous. Like people were going to laugh at us. So that we were not looking serious because we didn't have the background. We had a PhD, of course, but not in this field at all.
Uh-huh.
But we realized quite quickly that people in neurobiology were actually quite open to our ideas, that they were not ridiculous, they were just unknown things. So giving up, not really, because it's always interesting to we always have new ideas of experiments to do and things to refine. We are engineers. We love make things work.
Yeah.
We take it as a big engineering problem.
And that sounds like a very big problem where there's no clear end. How do you keep your milestone celebration, and how do you check that you are on track with your science and project?
Yes, that's a very good question. First, we fix always very modest objectives. We do experiment very, very close. Also, we take interns. This make sound like a detail, but it's not. So our master students are doing working in neurobiology. So we always have fresh ideas coming in. So every 6 months we have a new intern, and we have 2 meetings a day So it's always refreshing the ideas, testing experiments, and concluding, planning next experiments, and so forth. So the way we work.
Wow, and are you bootstrapping or fundraising, or how do you go through this journey?
Fundraising.
How is that? Because it sounds like it's such a demanding lab work and strategic, always experimenting, and then you have to fundraise, and you have to come to investors to explain something that sounds complex, at least for me. And then it comes to just simple, hey, everything is like super fast, cheaper execution, cheaper in the short term, etc. So how is that working for you?
So first, we have a lot of investors who contact us. Okay.
Okay, cool.
Around
That's
the
a
world. Okay.
good problem to
But
have.
no. A lot of investors discuss with us, but so far we signed with none of them.
Okay.
So ideally, what we are looking for is the ideal thing would be 50 million Swiss francs. Okay, about 50 million euros once and for all. Okay, and then we are set up for 10 years for our full research. Right now, we were not able to find investor profile that were matching what we want. So that are ready to do deep tech long term in this field. So until we find the right profile of investor, we're not going to take their money, and we are going to rely on our own funding coming from the other company that we founded that makes profits.
Okay, that's amazing. So you're doing a proper matchmaking and you're not in a rush and you have a great opportunity to actually choose the right investor who wants to contribute to the science and to further growth.
Yes, and
That's
that's
really
a
good.
very rare luxury. And I hope the investors at the end will come from Europe. Based on my statistics, they may not, because I would say 95% of the investors I'm discussing with are not from Europe, but we'll see.
Okay, okay. That is pretty cool. So you've been through quite some exciting scientific and entrepreneurial journeys, and it seems like you're a person who has a lot of courage to change, to learn, and to build and fail. Well, also now since I learned that you're a windsurfer who likes the wind, so it also gives a good picture, right? That a lot of windsurfers, kitesurfers are reckless and they're just going for the goal, which seems potentially maybe not possible. If we will look back to the early days of you, younger Fred, younger self, what kind of advice would you give to yourself or a learning to follow, perhaps?
I think it's very important to do what inspires you, no matter what the other people tell you. Okay, because if you do what inspires you, it may be hard to make a living out of it. Okay, that's something else, but at least your life somehow makes sense. Because and if you don't work on your dreams, you will work for the dreams of someone else. So it's your choice.
Have you ever worked for someone else, actually?
Yes, but pretty unsuccessfully, I would say.
Why was that? Tell me, Fred, why was that?
No, but it was just after the PhD. Well, the co-founder of Forest Park and myself, we worked for another company, and they said that because we invented some technology in signal processing, that they would give us some shares, but they didn't. So we quit and we created our.
So where did you get your entrepreneurial mindset and thoughts? Because usually what we have in the deep tech and the science world, that people are working on a lot of patents and a lot of researches, and they not always want to commercialize their solutions, or they're not that good entrepreneurs and business people. So they always need someone from different environments. How was in your case?
Well, first in the lab where we were at the PFL, the professor was very much startup oriented. I would say half of
Okay.
the PhD made a startup at the end. And as a researcher and a scientist, I quite believe that or an engineer, if you do something and you're able to exchange this thing for some money, to trade it for some money, it's good. That means that what you did is useful. Okay, and I think in life, being useful or doing useful thing is a very good thing. Okay, very pleasant thing, and one proof and of usefulness is the price to which you can sell it. And that's why also we have a lot of patents. We love patents. Okay, we patent a lot of technologies, a lot of ideas, and I think this This is the whole thing, you know, you invent things, you patent, you make money out of it, and you do it again. That's a wonderful cycle.
Okay. And I have a few more questions for you, actually, Fred. They're a bit like spread out. So one of them, going back to those organoids who are alive, right? So my question is, so do those organoids ever die, or what happens with them?
Well, we believe they die. So we consider that they die when they have no electrical activity that we can monitor anymore. It's the same with the human beings, by the way. And so some die after a few days, sometimes after several months. We just had one who died last week and after more than 7 months of life. So it was the absolute record. Broken just 1 week ago. So, and yes, it's a concern. We want to increase the lifespan of our brain organoids. Particularly, you know, there are 2 steps. We keep them in orbital shaker separately in the dark, and then we take them and we put them on electrodes. When they are in maintenance mode, we can keep them for years. But as soon as we start to exchange information with them, they will die in a number of weeks. Okay, and this is the big thing on which we need to work.
Okay. Wow, that's interesting. And you mentioned also that you like sci-fi a lot, and perhaps you're reading quite some sci-fi. Do you see any parallels between some kind of sci-fi literature you're reading, let's say about neuron, about, I don't know, the brains and the future with the work you are doing? Is there some kind of reflecting parallels in that? Or something that inspires you to adjust your research?
I think if I talk about Arthur C. Clarke, for instance, was really for me the master of thinking out of the box. And this is what is wonderful with science fiction. And I love the idea of, imagine that you're in space, you're sitting in space, you look at the Earth 100 million kilometers away. It looks like a very small blue ball. From this perspective, what you are doing, does it still make sense? And if it does, that makes sense for me.
Okay. You just inspired me to a bit sit down, meditate, and zoom out and review the perspective of the things I'm doing. I hope for some other people as well. Talking about, we're getting closer to the end, and I have a couple of more questions about also your research and maybe more about your journey as a founder, scientist, etc. So what's been most surprising discovery so far in your research?
In research on the neurons?
Yes, in the research on the neurons.
I've been very surprised. The first, you take cells, okay, neuron cells, directly from liquid nitrogen. Okay, and you thaw them, so you bring them to room temperature and they live again. This is already a small miracle. When you do this, they are perfect sphere of 20 microns of diameter. And you put them on plastic surface and suddenly they change the shape. They become like, you know, this kind of shape that we see for neurons.
Yeah.
And if you have several of these neurons, they will try to connect them between them. And, you know, they don't have legs, so that they cannot move normally, okay? Neurons, okay? But they have so-called axons and dendrites, which normally are used to communicate, okay? Not to move. But what neurons do is that they use the neurons and the dendrites to walk on the surface in order to meet together and to connect. That's incredible. And that's a spontaneous behavior. And after some time, you see some electrical activity which is coming. This is all a series of miracles, spontaneous miracles, that you reproduce yourself in the lab. And that's just incredible.
That's truly inspiring. And it's very inspiring to also see your eyes shining and being alive from when you're sharing what you're working on. So for the people who are listening, usually we finish the episodes with some kind of inspiring either quote or a question to ponder through the day after they listen to the episode. So maybe you could share a question for the audience related to entrepreneurship, health, philosophy that maybe they can ponder through.
A question?
A question regarding anything about the humanity, life, curiosity, cells, that they can continue thinking about after hearing a conversation with you. Maybe some inspirational thing to reflect on. Can see that.
There are so many directions in what you're
Just one, the first one that comes to your mind, something that people can reflect and question.
It's very much about fascination and curiosity for what exists. It's incredible what we have around us, which is incredible. So we're surrounded by incredible things. So that would be my thing.
Okay, so we're surrounded by incredible things, so I think everyone will take it from here. And Fred, one more question for you. Where do you find your inspiration, and how do you keep such a sparking eyes in such a busy world?
I really love science. I love knowledge. I love doing things which have never been done before. Even better, I love doing things which have never been thought before. And this is really what inspires me.
Beautiful. So I wish everyone got some inspiration from the episode today. It was Fred Jordan from Final Spark, and he just shared with us some scientific truths, experiments, and the futuristic things. And I invite everyone to check out their live graphs and their work. I'll leave the links in the show notes. And Fred, thank you so much for joining today, Perception Paradox. It was a pleasure.
A shared pleasure.
All right, I'm stopping the recording.